Welcome to Brain Vision.
Probably we're going to talk about the magnetic force on a wire. So suppose that we have a wire that has a current I, carries a current I, and has a length L. And also assume that we have a magnetic field. Let's say that the magnetic field is pointing in this direction here. So the magnetic force, the total magnetic force F that's exerted on the wire is equal to B cross I times L, where the cross here is the vector product. Okay, so we have to suppose in our problem that we have a wire that has a length of 2 meters and a mass of 150 grams. And this, we have that at this point, the magnetic field of the Earth, that is equal to 0.55 gauss, that is 0.55 times 10 to the minus 4th Tesla. This is the magnetic field of the Earth, and it is horizontal. So I'm going to assume that this magnetic field is pointing from west to east, like this. Okay, this is the magnetic field. And we have a wire. I'm going to assume that the wire is also on the horizontal but perpendicular to the magnetic field, so it is entering the screen. And we want the force on the wire to be enough to counterbalance the gravitational force so that the wire stays put, stays at rest. So basically we want the magnetic force to be equal to mg. And the magnetic force is B times the current I times L, since the magnetic field and the current I are perpendicular. And our goal is to find what is the current necessary. So the current I is equal to mg divided by BL. Now m is 150 grams, so 1.15 kilograms, times gravitational constant of 9.8 meters per second squared, divided by B, that's 5.5 times 10 to the minus 5 Tesla, times the length L of 2 meters. So I is equal to 1.34 times 10 to the 4th amperes. Okay, this is the electric current necessary. And the exercise asks us if it seems likely that the wire will be able to support this current. And the answer is no. So it's unlikely because this is a very large current. Then in question B, we have to say where this current should be pointing to. So remember, we need the force caused by the magnetic field to be pointing upwards, so that it counterbalances the weight that the Earth exerts over the wire. So for that to be true, I, that is the vector current, must be pointing towards that is that it must be entering the screen, as shown here in the figure, so that when we make the right hand rule, and make the cross vector, the cross product, I'm sorry, between B and I, we obtain that the F points upwards. So we want I to be pointing towards the screen, at least in this setup that we created here. And this concludes our exercise.